The bridge opens at 5:47 a.m., traffic flows, commuters look ahead, nobody looks down. But 12 hours before the first car crosses, a crew of 4 has already been on that bridge. They did not arrive with fanfare. They arrived with torches, clipboards, and measuring instruments. They arrived in the dark. Bridge and tunnel inspection is one of the least visible safety systems in modern infrastructure. It operates on cycles: daily visual checks, quarterly detailed surveys, and full structural assessments every 2 years or less, depending on the classification of the structure. Every cycle generates records. Every record feeds a database. And somewhere inside that database, a decision is being made about whether the bridge you will cross tomorrow is still rated for the load you will place on it. The tools have changed over decades, but the fundamental act has not. An inspector must look at a structure up close, not from a moving car, not from a photograph, from a few centimeters away with a torch, a crack gauge, and trained eyes. The body of the inspector becomes part of the process. They must climb, reach, hang, and hold, and record what they see with precision while doing it. In most countries, bridges are classified by condition rating, a numerical score from 1 to 9, or a similar national scale, where 9 is new construction and 1 is critically deficient. The number is not abstract. It determines maintenance priority, budget allocation, and in extreme cases, load restriction or closure. The rating changes slowly, but it does change. A bridge does not fail suddenly without warning. The structure sends signals first: microcracks in the concrete deck, corrosion creeping along the rebars, settlement in the abutments. The role of the inspection cycle is to read those signals before they become something larger. The system is designed around early detection. The problem is always finding the signal in time. Tonight, the crew operating below the Mercantile River Bridge is led by a senior inspector named Khan. He has been doing this for 19 years. He knows this bridge by memory. Every pier, every expansion joint, every drainage point. When something changes, he notices. That familiarity is not incidental. It is intentional. Long-term inspection teams are assigned the same structures for continuity of knowledge. The bridge inspection process begins well before anyone sets foot on the structure. It begins in the office. Engineers review the previous inspection report. They note what was flagged, what was monitored, and what was resolved. They cross-reference weather data, freeze-thaw cycles, flood events, unusually heavy traffic periods. A bridge carries history in its material, and the inspector arrives already reading it. Traffic management must be coordinated before any inspection begins on a live bridge. A lane closure request goes through Transport Authority approval. Signs are positioned. Variable message boards are updated, police or traffic officers may be deployed, and all of that coordination takes place days or weeks before Khan and his crew ever put on their harnesses. The paperwork precedes the work. The inspection vehicle itself is often a bridge inspection unit, a truck-mounted articulated arm that can extend beneath the deck and position an inspector in a work basket below the structure. The operator at the controls monitors both the structure and the inspector in the basket simultaneously. It is slow, deliberate work. The arm moves in increments. Each position is held long enough to allow thorough examination. Below the traffic, below the water line in some cases, the structural elements of a bridge tell a different story than the surface does. The deck might look functional, the paint might be fresh, but in the substructure, the piers, the pile caps, the bearing pads, the real conversation between the bridge and its environment is happening. Water, salt, load, and time, those are the 4 forces every inspector is trained to read. Bearing pads are among the most critical and least discussed components of a bridge. They sit between the superstructure and the substructure, absorbing movement, thermal expansion, wind sway, seismic activity. A bearing pad that has rotated beyond its tolerance, cracked or extruded, is a structural event. It changes how load is distributed across the entire span. Woo! Finding it before failure is the exact purpose of the inspection cycle. Khan stops. He does not say anything immediately. He crouches near a pier cap and examines a horizontal crack that was not in last year's report. He measures it. He photographs it. He marks its location on a sketch grid. The crack is 3 millimeters wide and 40 centimeters long. Those measurements will travel up the chain before morning. The structure is still safe, but the record has changed. Tunnel inspection presents a different set of operational constraints. The environment is enclosed. Ventilation is managed. Traffic, if present, is controlled in cycles. And the inspection team operates inside a space where every system, lighting, drainage, emergency egress, fire suppression, structural lining, must be assessed simultaneously. A tunnel is not one asset. It is dozens of overlapping systems sharing the same confined space. The tunnel lining is the first thing inspected. A continuous survey of the concrete surface for spalling, delamination, leakage staining, and crack patterns. The inspector moves along the lining systematically, section by section, referencing a grid map of the tunnel's interior. A good lining inspection takes several hours. There is no shortcut. The concrete does not speak until someone listens closely. Water infiltration is the primary enemy of tunnel integrity. Where water enters, chemistry follows. Carbonation, chloride ingress, and sulfate attack all begin with a water pathway. An inspector finding a damp patch on a tunnel wall is not finding a cosmetic problem. They are finding the entry point of a process that, if unchecked, restructures the concrete at the molecular level over years. The damp patch is the early chapter of a much longer story. The drainage system within a tunnel is one of its quietest operating components. A network of sumps, channels, and pumps manages whatever water enters the tunnel environment, from road surface runoff, groundwater infiltration, and spill events. If the drainage system silts up, blocks, or pump fails, water accumulates. That accumulation affects road safety, structural chemistry, and electrical systems simultaneously. The inspection of drainage is its own subcategory, performed in segments. The inspection of tunnel lighting is often conducted as a separate pass. Every luminaire is checked for functionality, lux level output, and physical condition. Dimly lit zones within a tunnel are not merely uncomfortable for drivers, they represent a safety-critical failure. Emergency lighting, exit sign illumination, and the transition zones at portals all require specific minimum standards. Light is not ambient in a tunnel. It is engineered, and it is audited. By 1:15 a.m., the tunnel team has completed the northbound inspection run. The team lead, a civil engineer named Fatma, compiles the night's observations into a structured condition report on a rugged field tablet. 47 items recorded, 6 requiring near-term follow-up, 2 flagged for engineering review within the week, none requiring immediate closure. The tunnel will reopen at 4:30 a.m. on schedule. Emergency egress systems are inspected with particular rigor. In a tunnel fire event, the pedestrian escape routes, emergency doors, and cross-passage connections are the difference between evacuation and catastrophe. Each door is physically tested, opened, checked for free operation, seals examined, hardware function verified. This is not a bureaucratic checklist. The people who built the inspection protocol designed it after studying what happened when these systems were absent. Not all inspections are conducted by people in direct contact with the structure. Technology has introduced a parallel layer of assessment. Acoustic emission sensors monitor for crack propagation in real time. Vibration monitoring arrays track modal frequencies to detect stiffness changes. Ground-penetrating radar units scan bridge decks for voids and rebar corrosion invisible to the eye. The human inspector and the sensor network operate together. Neither replaces the other. Drone inspection technology has changed the access equation for tall structures. A cable-stayed bridge tower, a suspension bridge main cable, or a high-arch rib that would previously require an expensive rigging and rope access operation can now be visually assessed by a drone-mounted high-resolution camera. The drone does not replace the close-up inspection, but it performs the reconnaissance pass, identifies areas requiring closer attention, and reduces the time inspectors spend in elevated risk positions. A rope access team operates on a different tier of the inspection hierarchy. Where drones cannot touch and super trucks cannot reach, the rope access inspector goes. Suspended from an anchor system at the top of the structure, the inspector descends along the face of a tower, the soffit of a high arch, or the underside of a span with a precision that no mechanical arm can fully replicate. The work requires specialist training that combines structural knowledge with vertical rescue competency. The physical experience of rope access inspection is one that few outside the profession fully understand. There is no solid floor. The wind becomes a variable. Every movement must be controlled and intentional because any uncontrolled swing is a safety event. The inspector manages the rope, manages their body, manages their tools, and simultaneously maintains concentration on the structural surface in front of them. The mental load is as significant as the physical one. Bridge inspection is not only about finding defects, it is equally about confirming that the structure is performing as designed. An inspector who completes a full survey and finds nothing significant is not wasting time. They are generating a baseline record, the documented proof that on that date, in those conditions, the structure was performing within its expected parameters. That record is as valuable as any defect report. By 3 a.m., the bridge inspection team has moved from the substructure to the expansion joints, the segmented connections between bridge spans that allow thermal movement. Each joint is checked for debris accumulation, seal continuity, and lockup risk. A locked expansion joint transfers load to adjacent structure in ways the original design did not anticipate. It is a quiet risk, one that builds over cycles. The inspection of bridge railings and parapets is often delegated to a separate crew working the surface level. It is less dramatic than the understructure work, but the consequences of a degraded parapet are immediate and human. These are the elements between a vehicle and the edge. Every weld, every anchorage, every post is tested for mechanical integrity. The aesthetic condition is secondary. The structural connection is primary. Seismic assessment has become a more prominent part of bridge inspection practice in many regions over the past 2 decades. This includes both evaluating whether older structures were designed to modern seismic standards and identifying whether installed seismic isolation or restraint systems are still performing as required. A bearing pad that has shifted, a hold-down bolt that has loosened, a seismic bumper that has degraded. Each item carries a risk profile calibrated against the seismicity of the region. At 4 a.m., the inspection teams begin their demobilization. The equipment is packed, the work basket is retracted, the cones begin to come in. But the documentation work continues for another 2 hours in the operations vehicle. Every observation must be referenced to its location code. Every photograph must be tagged. Every defect must receive a priority classification. The physical inspection is half the work. The record is the other half. What happens after the inspection data is collected is a process that most people never see and rarely think about. The raw field notes and photographs go to a structural engineering team. Defects are graded by severity, location, and trend. A new crack in a non-critical component might be classified as monitor and review. The same crack in a primary load-bearing element might trigger an interim loading restriction within 24 hours. The grading determines the urgency of the response. There is a category of bridge that demands a different inspection cadence, the fracture critical bridge. These are structures where a single member failure without an alternative load path could cause partial or total collapse. Steel bridges with non-redundant tension components, tied arch bridges, certain truss configurations. Fracture critical designation means mandatory inspection every 24 months without exception and heightened scrutiny on the designated critical members each cycle. The maintenance team that responds to inspection findings is separate from the inspection team. They receive work orders generated by the engineering review, ranked by priority, a drainage clean, a joint reseal, a concrete repair patch, a bearing replacement. Each task has its own mobilization sequence, traffic management plan, and material specification. The inspection triggers the maintenance. The maintenance closes the loop. And then the inspection cycle begins again. Back inside the tunnel, a separate inspection priority governs the ventilation system. Tunnels above a certain length require mechanical ventilation, either longitudinal jet fans, transverse duct systems, or a combination. In normal operation, these systems manage air quality and temperature. In a fire event, they become critical to life safety, managing smoke movement, maintaining breathable air in evacuation zones, and supporting the fire suppression sequence. Every fan, every damper, every duct connection is part of the safety system. Fire detection and suppression systems are among the most safety-critical components in a tunnel and among the most technically complex to inspect. Linear heat detection cables, CCTV fire detection systems, and deluge nozzle arrays all require functional testing under controlled conditions. The inspection cannot simply be visual. Each device must be triggered, and its response must be logged against response time thresholds. The system that protects a tunnel full of people must be proven, not assumed. The control room of a major tunnel operates around the clock. Traffic cameras feed live video to operators who monitor flow, incidents, and environmental conditions. Variable speed signs, traffic lights, and lane control signals can be adjusted remotely. During an inspection window, the control room does not stand down. It maintains oversight of the entire facility while the inspection team works within it. Two different operational layers running simultaneously in the same space. There is another class of inspection that happens not on the structure itself, but in the water beneath it. Underwater inspection of bridge substructure is a specialist discipline performed by commercial divers or, increasingly, by underwater remotely operated vehicles. The environment below the waterline is often zero visibility. The inspector works by touch, by reference to pre-mapped pier geometry, and by a checklist developed from previous surveys. The work does not get easier with experience. It only becomes more systematic. River score is one of the most dangerous conditions a bridge foundation can experience. It is also one of the most invisible. When water velocity increases during a flood event, the riverbed material around a bridge pier erodes. If scour reaches a critical depth, the foundation loses bearing capacity and the structure becomes unstable. The only way to detect scour before failure is through regular underwater survey, measuring the riverbed around each pier and comparing it to the original design level. At a large infrastructure authority, the inspection database is not just a record-keeping system, it is a planning tool. Budget cycles are governed by the condition data it holds. A structure approaching a critical rating threshold triggers a capital works program. A cluster of similar defect types appearing across multiple structures signals a systemic problem, perhaps a materials batch, a design detail, or a maintenance practice that failed at scale. The database reads patterns that individual inspectors cannot. Among the most demanding aspects of inspection work is the communication of risk, translating structural condition into language that decision makers can act on. An engineer's condition report is a technical document. A transport minister's briefing is not. Somewhere between those two documents, a prioritization decision is made, and that decision allocates resources, defers work, or accelerates it. The inspector's findings do not make the decision, but they make the decision possible. The bridge is rated for 200,000 vehicles per day. On a Saturday in August, it carries 180 to 7,000. On a Tuesday in February, it carries 60 to 3,000. The structure does not know the calendar. It only knows cumulative load cycles. Each passage of a heavy goods vehicle generates a stress cycle in the steel and concrete. The number of stress cycles, not the calendar age, determines the fatigue life of a bridge. And fatigue is one of the defect categories that inspection monitors most closely. The inspection of historical bridges presents a separate set of technical and institutional challenges. Many historic stone arch and cast iron bridges are still in active service, carrying loads many times greater than they were originally designed for. Their inspection requires an understanding of 19th century construction logic, how the arch transmits load, where the critical sections are, and how the materials behave differently from modern reinforced concrete. The inspector must read a different language. The shift changes at 6 a.m. The overnight inspection crew hands over to the day engineering team at the site office. The handover is not a conversation. It is a structured transfer of documented findings, flagged items, and incomplete observations. The incoming team needs to know exactly what was completed, what was left, and what requires immediate engineering attention. The handover document is the bridge between the night's work and the day's decisions. By 6:30 a.m., the bridge is back to normal operation. Traffic builds steadily on the approach roads. The barriers are gone. The inspection vehicle is parked kilometers away. The only evidence that something happened overnight is the fresh chalk marks on two of the pier caps, temporary location references for the follow-up maintenance team that will arrive next week. The bridge carries the traffic. The marks carry the record of the night. The inspection of a long tunnel is governed by a zoning system. The structure is divided into numbered sections, typically 20 to 50 meters each, and each section is assigned its own inspection record. This means a tunnel 3 kilometers long will generate 60 to 150 individual zone records per inspection cycle. The granularity is deliberate. A defect must be traceable to a specific location so that repair crews can find it, and so that trend analysis over multiple cycles can show whether a defect is localized or propagating. What the records show, year over year, is that the same types of defects tend to occur in the same types of locations. Drainage channels block at low points and bends. Lining cracks appear first at construction joints and around embedded fittings. Corrosion initiates where water accumulates in steel features. The patterns are not random. They follow the physics of the structure, and experienced inspectors learn to weight their attention accordingly. Some locations require more scrutiny than the grid alone would suggest. Some of the most consequential tunnel inspections happen after exceptional events: a vehicle fire, a flood inundation, a seismic tremor. These post-event inspections follow an accelerated protocol. The structure is assessed within hours of the event. Every fire-exposed zone is examined for heat spalling and structural damage to the lining. Drainage systems are checked for debris loading. Instrumentation is reviewed for anomalous readings. The inspection is not about routine condition. It is about whether the tunnel can reopen. Tunnel portal zones. The transition areas where the confined tunnel environment meets open air are subject to a specific set of environmental stresses not present in the body of the tunnel. They experience greater temperature cycling, solar radiation, wind-blown abrasion, and seasonal freeze-thaw cycles. Portal wing walls, overhead lintels, and approach culverts require separate inspection attention. Inspectors familiar with tunnel bodies who are unfamiliar with portal zone degradation mechanisms can underestimate what they find there. The question people most commonly ask about bridge and tunnel inspection is simple: does it work? The answer, measured against the statistical record of structural failures in countries with robust inspection regimes, is yes, but conditionally. The system works when it is adequately resourced, when inspection cycles are maintained without deferral, and when the findings are acted on rather than filed. When those conditions break down, the inspection record becomes a document of what was known, and when, that record has weight in a different kind of inquiry. The coordination between transport authorities, engineering consultants, maintenance contractors, and emergency services is one of the less examined aspects of the inspection system. A bridge inspection program is not planned by one organization. It involves client-side asset management teams, engineering review panels, procurement departments, and traffic management coordinators. The sequence of activities that puts Khan on a bridge at 1 a.m. began in a planning meeting 12 weeks earlier. The work is the visible tip of a logistical system. The professional training pathway for a bridge inspector involves formal engineering education, structured field experience, and, in most national systems, a certification or accreditation process that must be maintained through continuing professional development. The knowledge base required spans structural engineering, material science, GE, technical behavior, hydraulics, and the history of construction practice. A newly qualified inspector does not inspect alone. They begin as part of a supervised team reading the structure alongside someone who has read it many times before. There is a rhythm to the inspection year that those inside the profession recognize. Spring brings the post-winter assessment cycle, freeze-thaw damage, drainage repairs, expansion joint checks. Summer is the prime season for high-access work. Rope access, underwater dive inspections, major snooper runs. Autumn brings the pre-winter preparation cycle, drainage clears, joint reseals, anti-skid surface treatments. Winter brings reduced access, increased caution, and the knowledge that every cold night is doing work that will need to be assessed in spring. The night before a major inspection window, a team coordinator named Levent runs through the checklist one more time. Equipment loaded. Traffic management, confirmed. Engineering brief, reviewed. Emergency contact list, current. The preparation is not anxiety, it is protocol. Every variable that can be controlled in advance is controlled. What cannot be controlled is what the structure will show them in the dark. That is the part of the work that no checklist can preempt. High-speed rail tunnels introduce a further layer of inspection complexity. The aerodynamic environment within a tunnel used by high-speed trains creates pressure waves that cycle through the structure with every passage. These pressure differentials affect expansion joints, drainage covers, and surface fixtures. The inspection of a high-speed rail tunnel cannot happen while trains are running. Access windows are typically 4 hours in the early morning, and the planning to secure those windows involves railway operation controllers, timetable management, and infrastructure maintenance teams coordinating. A suspension bridge main cable is among the most difficult structural elements to inspect. The cable is composed of thousands of individual high-strength steel wires bundled under a wrapping and weatherproofing system. Beneath that wrapping, the wires are invisible. Moisture that penetrates the system initiates wire corrosion from the inside, damage that only becomes apparent when the cable is opened. Main cable inspection programs require strategic dehumidification, periodic panel opening, and wire-by-wire sampling across the full cable length. The human cost of inspection work is not dramatic in the way that construction accidents are dramatic. It accumulates over a career in a different way. Inspectors work in confined spaces, at height, in cold and wet conditions, in atmospheres with variable air quality. Occupational health monitoring is part of the professional framework in well-managed programs, baseline health assessments, PPE compliance, and documented exposure records for hazardous environments like lead paint structures and asbestos-containing materials in older infrastructure. At 5:30 a.m., the tunnel reopens. The variable message boards on the approach roads switch from closed. Inspection works back to normal speed limit displays. Operators in the control room confirm camera feeds are clear. The first vehicles entered the portal. Inside the tunnel, the only evidence of the night is cleaner drainage channels, a repaired strip of joint sealant in Sector 14, and a set of digital records that no driver will ever see. Records that say the tunnel was examined and passed. Outside the tunnel, the inspection vehicle drives back along the service road to the depot. The equipment will be cleaned, calibrated, and ready for the next deployment. The inspection records from tonight will be uploaded to the central database before noon. The maintenance work order will be generated by Thursday. And in 24 months, the cycle begins again. The same tunnel, the same team, the same systematic examination of a structure that most people will cross without a second thought. In some jurisdictions, the public has partial access to bridge inspection records through Freedom of Information frameworks. A citizen wants to know the condition rating of the bridge they cross each day, can, in theory, request the data. Few do. But the fact that the data exists That it is collected, maintained, and accessible, even theoretically, is a function of the inspection system that rarely receives recognition. The record is not just an engineering tool. It is a form of accountability built into the physical structure of civil society. Bridge and tunnel inspection has evolved significantly over the last 20 years, and it continues to evolve. Machine learning algorithms are being trained to identify defect signatures in image datasets, not to replace the inspector, but to assist in the pre-screening of thousands of photographs generated per inspection cycle. Digital twin models allow structural engineers to visualize real-world sensor data within a three-dimensional model of the structure, observing how the bridge or tunnel is actually performing against its theoretical design predictions. The technology changes. The fundamental task does not. The overnight inspection of a long bridge, the kind that spans a major estuary or connects two land masses across open water, introduces the additional variable of marine environment. Salt, air, tidal action, biological fouling, and storm exposure operate simultaneously on the structure. Pier coatings are inspected for deterioration. Anode systems for cathodic protection are checked for depletion. Access to the offshore sections is tide dependent. The inspection program is written around the tidal window. The tidal window closes at 7 a.m. The inspection boat returns to its mooring. The pier has been assessed. The anode depletion levels have been recorded. The coating damage zones have been photographed. And a recommendation for spot repair on the south face below the splash zone will be included in the quarterly maintenance schedule. The estuary does not pause for any of this. The tides continue. The bridge stands. The system has done what it was designed to do. The inspection of pedestrian bridges and footbridges follows a parallel but different protocol. These structures carry far lighter loads but are subject to a dynamic loading condition that highway bridges rarely experience: resonant pedestrian excitation. A footbridge with a natural frequency close to the walking frequency of a crowd can develop oscillations that are unsettling and, in extreme design cases, structurally significant. Inspection includes assessment of dynamic behavior as well as static structural condition. The bridge that bounces slightly underfoot is not necessarily failing, but it is being listened to. Railway bridge inspection operates under a different regulatory framework than highway bridge inspection. The consequences of a structural event on a railway bridge are often higher. Speed, alignment requirements, the coupling of rolling stock, and the inspection frequencies reflect this. Many railway infrastructure owners conduct frequent visual inspections at short intervals, with detailed inspections at longer cycles and principal inspections involving full structural assessment on their own regulatory calendar. The data chain from railway bridge inspector to network safety manager is often more direct than its highway counterpart. At 8:30 a.m. on a Wednesday, somewhere on an urban commuter network, a bridge inspector named Elif is filing her inspection notes from a structure that 34,000 people crossed this morning. She did not inspect it this morning. She inspected it at 2 a.m. during a 40-minute possession window between two train services. The 34,000 people who crossed did not notice. They were not meant to. The work was already done. There is a particular kind of knowledge that long-service bridge inspectors carry that cannot be transferred through a report or a database. It is the knowledge of how a structure sounds, how a pier sounds when it is tapped, a sharp return versus a hollow note, how a concrete surface responds to a raking torch, the way light catches a barely visible delamination plane, how a tendon duct sounds when struck along its length, the solid return of a grouted duct against the void sound of an incomplete one. These are analog assessments carried in the inspector's sensory memory. The inspection of a bridge deck surface, the wearing course that vehicles drive on directly, is its own inspection domain. Rutting, cracking, potholing, and delamination of the wearing course can allow water into the structural deck below. The deck waterproofing membrane, invisible beneath the asphalt, is the critical layer. Its integrity is assessed through coring samples, ground-penetrating radar, and in some cases, infrared thermography, which reveals temperature differentials indicating delamination or water-filled voids under the surface. The road surface is a structural interface, not just pavement. A condition rating of 4 on a 9-point scale does not mean the bridge is about to collapse. It means the bridge has advanced deterioration in primary components that has substantially reduced its safe load capacity or load carrying capability, and that major rehabilitation or replacement is required. That distinction between dangerous and deteriorated is one that inspection systems are designed to communicate carefully. Public perception of bridge condition and engineering reality are not always aligned. The language of infrastructure condition is technical by necessity. Among the less visible roles in the inspection ecosystem is the data analyst, who works in the infrastructure management office, never visiting the structures. Their work is to find meaning in the condition data across an entire asset portfolio, tracking deterioration curves, projecting maintenance costs, modeling the effect of different budget scenarios on the future condition of the network. The field inspector sees one bridge at a time. The analyst sees the whole network at once and tells the story of what the network will look like in 10, 20, 30 years if nothing changes. The physical act of reaching the underside of a bridge in a difficult location is sometimes its own undertaking. For a viaduct above a valley, a river crossing in a remote gorge, or a marine bridge over deep water, the logistics of access can take more planning than the inspection itself. Temporary scaffold towers, barges, helicopters, and cable car systems have all been used as access platforms. The inspection is the purpose. The access system is the problem to be solved first. The inspection of a tunnel through mountainous terrain introduces geological variables absent from cut and cover or bored tunnels in stable ground. Rock movement, groundwater pressure, fluctuations, and fault zone activity can all affect the tunnel lining in ways that are not governed purely by traffic load. Geological monitoring, convergence measurement, piezometric, groundwater level tracking, and rock bolt load monitoring is integrated into the inspection framework for mountain tunnels. The mountain is not a passive boundary. It is an active structural participant. By the time most commuters are sitting at their desks at 9 a.m., the morning's inspection work has been completed across a dozen structures in a regional network. Traffic counts are running normally. Load restrictions have been updated where required. A maintenance work order has been raised for 3 items. One engineering review meeting has been scheduled for later in the week. The night has already happened. The morning carries its results invisibly in the condition of the infrastructure around it. In the quieter hours of mid-morning, the documentation process continues. Inspection reports are peer-reviewed before they are finalized. Another engineer reads the findings, checks the condition coding, and confirms the priority classifications. This is a quality assurance step, not a formality. A single misjudged priority rating can defer a repair that should happen soon or accelerate a repair that is not yet needed. The peer review catches what the field visit cannot. The assumption that a familiar feature has not changed. Kyan closes the inspection file on his workstation screen. 19 years of these files. 19 years of the same structures. He knows the inventory of defects across his territory better than most people know the layout of their own homes. Not because it is unusual work, because it is careful work. Repeated. The work is never finished. The next cycle is already scheduled. But for now, the morning shift has started, the coffee is warm, and the bridge outside his office window is carrying traffic, as it should. The work of bridge and tunnel inspection is not heroic. Nobody makes films about it. Nobody finds it in the news unless something has gone wrong. It operates in the margins of public awareness, conducted in nighttime windows, underground, at height, in water, between train movements, in the hours when the infrastructure system is least encumbered by its own users. The people who do this work know its value. So do the engineers who read their findings. The structure itself does not care whether anyone notices. It simply continues to carry the load placed upon it for as long as the system behind it holds. Somewhere tonight, a 4-person inspection crew is loading equipment into a vehicle in a depot yard. Their shift starts at midnight. The structure they are going to, a highway bridge, a transit tunnel, a railway viaduct, does not know they are coming. It will simply be examined, recorded, and returned to service. And somewhere else tonight, the same thing is happening. In another city, on another structure, in a different language, by a different crew. The system runs continuously, around the clock, without fanfare, and largely without notice. That is what makes it work. Under this video, there's a subscribe button. It's a small action, but it helps reveal the systems most people never notice. If you're curious about how everyday life actually functions, how the infrastructure around you is maintained, examined, and kept in service, consider subscribing. And tell us in the comments, where are you watching from? Have you ever worked on a bridge, in a tunnel, or behind the scenes of a system like this? We read every comment. The systems you cross every day are worth knowing.